In this video, I'm going to show how you can take a cooling tower with a given set of design parameters and model how it should perform when the operating conditions of the system change. So for example, once you have this model built, you'll be able to change the various outdoor air conditions that you might see over the course of a year. You can change the fan speed of your cooling tower. You can change the speed of your tower water pump. And you can change the return water temperature that you get from your cooling loads and model what your supply air temperature, or sorry, what your supply water temperature would be. And then you can do a similar model, and instead of manipulating the fan speed to see what temperature water you'd get, you can change your supply water temperature set point and calculate what your tower fan speed should be, as well as fan power and pump power and everything you'd want to know about a cooling tower system. I have not found a lot of resources out there that show how to do this in the detail that I'm going to share. So that's why I'm trying to share what I've come up with and how I've compiled various sources together to put this together. It's not a perfect model, but it does align well with real world data that I've compared it with, and it gives similar results to performance calculators that are supplied by cooling tower manufacturers. So no model is perfect, but some are useful, and I find that this is a useful one. I'm going to assume that you already know some of the basics of what a cooling tower is and how they operate. So we're just going to jump right into some of the technical analysis of cooling tower modeling. And at the beginning, what I said is that you can do this model if you know the design performance characteristics of a cooling tower. And some of those design characteristics, and one that we'll use an example for, is something like this. You'll have a given set of outdoor air conditions that your cooling tower is operating at. A lot of times it's 78-degree wet bulb, and then some dry bulb temperature. The wet bulb's more important than the dry bulbs, you'll see. You'll have a given amount of water flow that you're cooling from some temperature that it enters the cooling tower at and some temperature that it leaves at. And your tower fan will have some design cubic feet per minute that it can move, or a volumetric flow rate that that fan's designed to pull through the tower. And with those known operating conditions, that known performance that it can achieve, as you start manipulating other design parameters, so as your outdoor temp changes, water temperature and flow changes, as your air flow changes, you can model how that tower will perform in those conditions. All right, so let's get into it. Here we go. We're going to start just with a simple cooling tower energy balance. What a cooling tower is doing is rejecting heat out of a stream of water. And so the energy balance of that water is written in this equation here. Your heat rejected out of the water, Q, is equal to the water mass flow times its specific heat times the temperature difference of the water as it enters and exits the cooling tower. We're dealing with imperial units in all these examples, so your C value for water is 1 BTU per pound per degree Fahrenheit. So this equation can just be simplified to M times delta T, or M dot times delta T is your heat rejection rate. And then on your air side, however much water you reject, however much heat you reject out of your water is going to be equal to the heat that's absorbed in the airstream. And so your energy balance for your air is the air, or the energy gained by your air is equal to your mass flow of dry air times your enthalpy difference of the air as it exits and enters the tower. So your air enters the tower at whatever your outdoor air conditions are, and then it's going to exit at some enthalpy where it's going to be, typically it's going to exit warmer and close to saturation. And it's going to exit with, obviously, a higher enthalpy than it entered with. Those are our two main energy balance equations. It's for your water and air. And the next step that we're going to do is we're going to simply take these equations, which are equal to each other. We're going to take the top one divided by the bottom one. And you'll see why you do that later. But what you get is this. Your mass flow of water divided by mass flow of dry air is going to equal your enthalpy difference of your air divided by your temperature difference of the water. And we call this ratio of your mass flow of water to mass flow of dry air, we call that the L over G ratio. And that becomes a really important parameter that we'll see in our model later. The units that we're going to deal with for each of these mass flow rates is pounds per hour. And so when you do your pounds per hour divided by pounds per hour, obviously you end up with a unitless number. So everything that we've talked about so far is relatively straightforward, but the next step is where it starts getting more complicated. So this equation right here, if you look up Merkel equation, Merkel, a guy named Merkel in the 1920s, I think, came up with this. What he basically says is that you can analyze the mass transfer and heat transfer of water through a cooling tower by looking at every small slice of the cooling tower and looking at the mass transfer of water into the air. And so for a small droplet of water at some point in the tower, the mass flow of that water droplet times the incremental temperature difference that it experiences will equal Ka times dV. Ka is mass transfer coefficient. dV is a small slice of volume of the cooling tower times H prime minus enthalpy of your air. And H prime is what the enthalpy of the air would be if it were saturated at the temperature of the water that it's touching. And then H air is your actual enthalpy of the air. So again, the left side of the equation is pretty straightforward. It's just saying your small slice of energy transfer from your water's perspective is going to be the mass of the water times the minuscule temperature difference for that little droplet of water. And that's going to be equal to a mass transfer coefficient times a slice of cooling tower fill volume times this enthalpy difference. And I'll say this again, H prime is the enthalpy of air if it were saturated air at the temperature of the water that it's touching. And H air is the actual enthalpy of the air. Down below, we define what all these variables are and what their units are. If you do more research into this, you'll find different units for K and V. Sometimes V will be, instead of volume in cubic feet, it'll be cubic feet per area. And then area will be square feet per cubic feet. So in any case, the units should all cancel out, and you should end up with this is a unit of energy, and then this is going to be a unit of energy. So this is our Merkel equation, and when we rearrange it, so that rather than looking at a small slice of a cooling tower and a single water droplet, you can integrate over the entire tower, and doing some algebra, what you end up getting is this. This equation here is KAV over L, where Ka is a mass transfer coefficient, V is the volume of the cooling tower, and L is our liquid mass flow rate that we talked about earlier. And this is called the characteristic of the cooling tower. This is a relatively constant number, and we'll talk about this KAV over L number later. But what that equals is from this equation here, it equals the integral of dt over that H prime minus H from your temperature of your tower water as it exits the tower, which is going to be cooler water, to your temperature of your water that enters the tower, which is going to be warmer water. So this integral here is, it's not just a straightforward equation. You're going to have to look up properties of air, and we're going to talk about how to do that next. I'll jump off the equations here, and we'll start talking about how you can practically do this. I guess one more point on this equation, though. What this says, and what fundamentally how a cooling tower works, this equation is saying that the driving force for heat transfer in a cooling tower is the difference in enthalpy between saturated air at the temperature of the water that it's touching and the actual enthalpy of that air. So when I say driving force, I mean what's causing that to change and at what magnitude. It's that enthalpy difference of air and if that air were saturated at the water temperature. So your driving force, for example, for heat transfer in a heat exchanger is temperature difference. your driving force for flow in a pipe is pressure difference. Well, in a cooling tower, your driving force for heat transfer is your enthalpy difference of air at its current conditions and if it were saturated air at the temperature of the water. I keep repeating that, but I'm just saying it because it's not intuitive, and it may help you visualize what's happening in cooling towers down the road. Okay, so let's talk more visually about this rather than just getting into equation forms. So we're going to move over to this table right here that I've put together. This is just a simple air saturation curve where at various temperatures of air on the x-axis, your y-axis is what the enthalpy of that air would be if it were saturated. And if you're familiar with a psychrometric chart for air properties, it's basically the same shape of that curve, except instead of on our y-axis, instead of showing humidity ratio, we're showing saturated enthalpy. So these are just arbitrary temperatures that I've typed in myself. And then I'm calculating saturated enthalpy based on some custom psychrometric macros. You can look these values up in a psychrometric chart, and it's the same thing as the way I'm just calculating it in the background with NAT in. So it's saying, what is my enthalpy if I know temperature and relative humidity and atmospheric pressure? And the temperature input is my arbitrary temperature that I just want to know what my saturated enthalpy would be. I'm saying relative humidity is 1 or 100% because it's saturated. And then my atmospheric pressure is 14.7 psi. If you change this pressure, your saturated enthalpy will slightly change with it, but we're just doing this for sea level conditions. Okay, so I do that for every temperature, and then I get this saturation curve. The next thing that we should do, so I guess real quick, why do we care about this saturation curve? Because that's what this H prime number is from our Merkel equation. H prime is all of these enthalpies on this saturation curve at these temperatures, and these would be the temperature of the water that the air is touching, if we're talking about H prime here. So let's go back to our made-up cooling tower example, and we'll look at some of the design parameters and then see where these values are coming from. So these are our design conditions for an actual cooling tower that I've seen in person and analyzed before. And it's rated to cool 1,000 GPM of water from 95 degrees down to 85 degrees at a 78 degree Fahrenheit wet bulb outside. And it can do so with a 94,000 CFM of airflow. With that, I guess before we get back down into the example, our L over G ratio, which is our mass flow of liquid to mass flow of gas, is going to be 1.27. That value typically ranges anywhere from about 0.8 to 1.4 is as high as I've seen it. The higher that number is, I guess the more efficient the tower would be, because that would mean you've got a lower airflow rate relative to your water flow rate. So 1.27, that's kind of right in the ballpark that we'd expect. All right, so let's get back down into our example. We've talked about our H prime saturation curve, where we looked at, based on some arbitrary air temperature, what is our saturated air enthalpy. If we're looking at this, how to analyze this Merkel equation graphically, we also need to find where this H air term is on our chart. And that H air that's the actual enthalpy of air as it's interfacing with the water. And it looks like this on this curve here. So this orange line is this same air saturation curve, but it's just zoomed in a little bit. And then this blue line here is our enthalpy path of our actual air. So our outside air starts here, and then as it goes through the tower, it's going to linearly increase its enthalpy until it exits the cooling tower. And so I made this chart by starting with our temperature of water going through the cooling tower. We know that it enters at 95 degrees because that's what it's rated to do, and then it's going to exit at 85. So I started from bottom, and then I went up. I just chose an increment of 0.5 degrees. You can make this increment whatever you want, but the more granular you get, the more accurate you'll be. But I find 0.5 gets you close enough for our purposes. So the water goes through the cooling tower from 95 degrees, and then it decreases its temperature until it exits at 85 degrees. And then for every water temperature, it's going to be interfacing with an air at some enthalpy. So the air enters the cooling tower at the outside air enthalpy. And I've just plugged in my conditions, and then my macro calculates what the actual enthalpy is. So it's based on a 95-degree dry bulb temperature outside, 75-degree wet bulb, and atmospheric pressure at sea level. And then as it moves through the tower, it gains enthalpy linearly based on the amount of heat that gets transferred to it. So your water is going to have some mass flow in this small delta T is going to transfer energy into your air based on these equations here. And you don't have to use the actual mass flows of water and air. You can calculate what the enthalpy gain will be based on this L over G ratio. So that's another reason this ratio is useful. You can just use this equation here and calculate what the step is in your air enthalpy increase row by row. So as your air moves through the cooling tower, its enthalpy is going to increase at the slope of your L over G ratio. So the slope of this line is actually this L over G ratio, and that just comes from our energy balance equation. So that's pretty handy. Eventually, it gets to this point where it exits the cooling tower, which is going to be this point right here. It exits the tower at this point where it's interfacing with the temperature of water that's entering the tower. So with that, now that we know the path that our air enthalpy takes as it moves through the tower, we can look at, okay, what is the area between these two curves on this chart here? And why do we care about that? Because if I jump down to this rearranged Merkel equation, that's going to give us our tower characteristic number. And it's not a straightforward what is the area between these curves. It is actually, as you see in the equation, it's the inverse. It's the integral of the inverse of that temperature or that enthalpy difference. And so the way we get that is simply by doing this. I'm going row by row and calculating what's my temperature difference divided by my enthalpy difference in saturated conditions and my actual air enthalpy. So let's do one for this row, for example. My dt over h prime minus h is going to be delta t, so whatever my little temperature increment is. That's why I said earlier, the more granular you are, the more accurate this gets. But here's our little temperature increment. This is our dt divided by h prime minus h. So h prime is going to be the enthalpy of air if it were at, so my inputs here are temperature and relative humidity. So my temperature is if that air were at the temperature of the water that it's touching. So that's this one right here. And then I've got 1 plugged in for relative humidity because that means it's saturated. So this enthalpy of air if it were saturated at the water temperature minus the actual air enthalpy, which is the enthalpy of the air that's touching the water at this particular point. So we just simply do that same equation for every single row. And if you sum it all up, that is the integral of this equation. So we're not doing any complex calculus or anything. We're just manually taking the integral by calculating this incremental dt over h prime minus h, and then summing them all up for every point in the cooling tower where the water touches the air. So I get a value of about 1.202, and that equals my KAV over L. That is my tower characteristic number there. So I've calculated my KAV over L to be 1.2 in this case. Now this is with a DT of 0.5. It's not super accurate. I have a built-in macro in the background that'll calculate it. So for this, we're doing it much more granular in the background where I'm doing, instead of, 20 steps that I do for DT, I'm doing, I think, 500 or so steps. So it's much more granular in the background. And I get a characteristic value of 1.208. Doing it this way gives me 1.202. So we're pretty darn close by doing it this way. The macro that does it in the background is obviously more accurate, but for our purposes, that's exactly how you can calculate the tower characteristic number. All right, so we went through all this. We started with the energy balance, got to this characteristic number. And if that's not making sense, I'm calling it a characteristic number because that's basically going to remain constant for the cooling tower for a given L over G ratio. And you can think of this kind of like a UA value for a heat exchanger if you're familiar with heat exchangers. It's a constant value that allows you to do calculations based on different conditions than your design conditions. Okay, now here's the problem, not a problem, but another nuance we need to look at is that this KAV over L characteristic number is only valid for a certain L over G ratio. So if we're running at our design water flow rate and our design air flow rate, then you're good to use this number. As outside air conditions change, you can solve for your water conditions by basically iteratively solving to give you the same calculated KAV over L that your design gives you. Problem is, we often like to vary the speed of our fan so that we can get energy savings. Sometimes we vary the speed of our pumps as well to get energy savings or to achieve certain process variables. So that L over G ratio is not always going to be constant, and that means your KAV over L characteristic is not always going to be constant. So how do we find the adjusted characteristic based on an actual L over G ratio? It comes from this equation right here, and I'll zoom in on it. This equation, any KAV over L, any characteristic number for your tower is going to be equal to C, which is a constant, times an L over G ratio to the power of M, which is also a constant. So M is always, I always use negative 0.6, and that's going to be good enough for most purposes. If you're having to be really precise, you can anecdotally find what that M constant should be based on some actual data. But for just doing some estimated part load modeling, use negative 0.6 and you'll be fine for M. Now C is going to be constant, but you need to calculate what that is for your cooling tower. So what you do to calculate what that constant C is, plug in your design characteristic number, your KAV over L design, divided by your L over G design to the negative M, to the M, which is negative 0.6, and that's your C constant. So once you know C, you can plug in any L over G ratio, and then you'll calculate what your characteristic would be based on that input L over G ratio. So that's kind of a lot, and let me say the purpose of this one more time. What we want to do is solve for how our tower is going to perform for various operating conditions. And the way that you do that is once you have a characteristic KAV over L to solve for, once you know what this needs to be, you'll iteratively change your supply and return water temperatures so that when you calculate this integral, it matches the KAV over L that you need to achieve. Hopefully that makes sense. Let's look at it graphically one more time. As this L over G ratio changes, and like we said, it's the slope of this line is equal to our L over G ratio. So if I manually force this, just for illustrative purposes, let's make this really high. I'm going to make this 3. And when I change this, the slope is going to go up. And even actually it crosses the saturation curve, which is not possible. So what would then happen? We know this isn't a valid path for it to take because it can't become more than saturated. So what would actually happen is that if this is your actual ratio, because you can manipulate the airflow to give you that actual ratio, but this condition is not possible because these water temperatures would not be possible. So what would effectively happen is this curve would have to shift to the right such that, one, it has to be under or touching the saturation curve at all points, and two, that dt over h prime minus h integral that we talked about has to satisfy what your KAV over L target needs to be. So this would shift to the right such that this would end up equaling 1.2 or whatever your KAV over L target needs to be. Hopefully that makes sense. And what I just said there is what our macro is doing in the background. We'll do a few examples of that in 1 second. Let's also look if we were to make this number very small. So if I make this 0.5, this is going to flatten out because our slope's going to get much smaller. And what does that mean if your L over G ratio gets really small? That would mean that your G gets big or your L gets small. So you decrease your water flow rate by slowing down your pump, or you increase G by speeding up your fan. So let's say one of those two happens, and now we're at a 0.5 L over G ratio. When that flattens out, you now have a much higher area under this between these curves. And so to make it smaller, to satisfy your KAV over L, this has to shift to the left in order to satisfy that. So what does that mean? That means that your temperatures, let's say you've got you know it's going to be a 10-degree delta, and this is going to shift to the left. That means that you're going to be supplying colder water out of your tower, and you're going to get colder return water from your process. And intuitively, that makes sense because what we said is to get this number lower, you're going to increase your flow rate of air through the tower. So if we increase our flow rate of air, we get colder water. That makes sense. Or if you slow down your flow rate by slowing your pump down, that also forces us to get colder water out of our tower. And that makes sense too. If you've got a lower water flow rate, it's got more resonance time to get cooled off. So intuitively, that makes sense that as you decrease this number, you get colder water. But mathematically, that's the reason. It's because this curve has to shift such that your calculated KAV over L number satisfies your Merkel equation. Hopefully that makes sense. That's kind of a mouthful. I didn't fully understand it the first time around. I had to do a lot of different examples for this to click. So let's go through and this is kind of the manual process of how to do it. In the background, I have some macros that are doing this for me. So if I look at my tower functions, I've got a bunch of code that basically does everything that I just described. So let's talk about let's change some values and see how the model changes, and then we can refer to the equations as to why that change occurred. So let's put these at the design conditions actually. So we said it's a 95 dry bulb, 78 wet bulb. Obviously it's designed for 100% fan speed, 100% pump speed. And right now the model is set up where you manually type in your return water from your process, and then based on your fan speed, it calculates a supply water temp. And it's doing this. Let's look at the inputs to this function. This function is just called, calc T water exit. So calculate my water temperature exiting from the tower. And if we look at the inputs, we can kind of cross-check this with the equations that we just talked about. So you need to know your dry bulb and wet bulb temperature outside. What that tells you is the density of air. And you need the density of air because we're also going to plug in the CFM of air. And if you take your CFM of outside air times the density, you're going to get a mass flow. You can also take dry bulb and wet bulb and get a humidity ratio. And so that not only tells you your density and lets you calculate your mass flow, but it tells you how much water vapor is in your air. So it tells you your enthalpy as well, which is a critical number that we use. And it also lets you segregate how much of that CFM is dry air versus dry air versus water vapor. Because anytime you're doing a mass flow of air times an enthalpy difference, you need to use the dry air mass only. You don't use the mass of water vapor in that air. So that's the first thing that the macro does. We're getting, and by the way, we're getting CFM from the percent speed that it's running at times the rated CFM. So let's go back to these inputs here. Next, we need our GPM of water. That's fairly straightforward. It's this number here, which is simply our pump speed percentage times the rated GPM. And that allows you to calculate mass flow. To go from GPM to pounds per hour for water, you simply multiply GPM times 500. So 1,000 GPM is going to be 500,000 pounds an hour. You need the inlet water temperature to the cooling tower, which is something that we manually set. We manually set it here in the model, and it's also just the design parameter. It says that if you've got 95 degrees coming back from your process or your cooling loads, then the tower can cool it down to 85 degrees. Okay, next is our KAV over L design number. And that number is being referenced right here. So we calculate this. There's a separate function in here that calculates this just straight up. And then we also have to reference our L over G design, which is right here. Now, why do we have our design characteristic and L over G ratio? It's because as you change your input flows of air and water, we're using these to calculate our adjusted KAV over L target. So that's being done in the background. And that's it. If you know these inputs, you can calculate an adjusted KAV over L and then numerically solve for what your exit water temperature needs to be such that your target KAV over L is satisfied. So that's what it's doing in the background. Let's change our outdoor wet bulb temperature to start. Let's make this, instead of 78, we'll make it 65. So as we decrease the wet bulb temperature, what happened? Our supply water temperature decreases. I think that's fairly obvious that would happen. So all things being the same, as our wet bulb temperature outside goes down, we can make colder water. That's pretty straightforward. Let's also assume that let's change this return water temperature so that we also have a 10-degree delta T on the water side, like we did in our design conditions. So in other words, this range, we want to keep it at 10. Let's see, if we've got a 10-degree range, what temperature of cold water can we get? And we'll calculate that using the solver here. So let's set, I guess we can do a goal seek here. So let's set that to a value of 10 by changing return water temp. What happens is if I were to have just changed it to be 10 degrees higher than our the supply water temperature we initially calculated, that would affect the actual supply water temperature. So this is a function of this. So that's why it's not a straightforward calculation. I can't make this reference this because they're a function of each other, and you get circular references. So it's unfortunately an iterative calculation, but it can be done with goal seek or solver. So keeping that design 10-degree range, if our wet bulb drops down to 65, we can make 75-degree water. What's interesting there is it's now, instead of a 7-degree approach, where our design was a 7-degree approach, so the supply water temperature we can make is 7 degrees higher than the wet bulb outside. In this case, Everything is equal. The range of the tower and the flow rates are the same. The only thing that changes is wet bulb. But when that wet bulb changed, our approach actually degraded a little bit. And if you've observed actual tower performance before, what you'll find is that as the wet bulb temperature outside goes down, the temperature of supply water you can make also goes down, but the approach degrades. It never is going to stay at exactly 7 degrees for your full delta T conditions. The rule of thumb is that it degrades by about half of a degree per wet bulb. Sorry, your approach degrades by about half of a degree for every 1 degree decrease in wet bulb temperature off your design conditions. So what does that mean? Our design wet bulb is 78, and we're looking at 65-degree wet bulb. So if we say 78 minus 65 is we've got a 13-degree drop in wet bulb temperature from our design. And so if we take 0.5 times that, 6.5, the rule of thumb says that our approach to wet bulb should go from 7 to 7 plus 6.5, so about 13.5. We actually achieved 10.5 approach, so the rule of thumb is a little bit conservative. Looks like we can do better if we actually model it. But that was kind of a side tangent. Don't worry about that. Let's look now if we were to change our fan speed. We already talked about that down below. I guess before we just change it and see the result, let's kind of predict what's going to happen. Looking at the equations, if our by dropping the fan speed, this G will go down, and so our L over G ratio goes up. If L over G goes up, the slope of this line increases, which decreases the area between these curves, which is our driving force for heat transfer. And so in order to maintain or achieve the area that we need to, if this slope is going to go up, then this curve needs to shift to the right. So that means that we should expect the temperature of our supply water to increase. So let's knock this down to 80%, and we should see this go up. And let's do the same thing again. Let's goal seek to keep the same range. So I want that to be 10 by changing my return water. And it finds an equilibrium point eventually. So now we're making 78-degree water instead of what we just saw a second ago at 100% speed was about 75. So as we drop, and we just talked about that kind of in a complicated way by looking at areas under curves on a chart. But the common sense approach is, yeah, if I slow my fan speed down, of course I'm going to get warmer water coming out of the tower. Duh. But just graphically and on an equation perspective, that's why it happens. Let's knock this back up to 100. So we've got, and let's make our range 10 again, just so we're always looking at kind of an apples to apples comparison. I want to set that to 10 by changing this guy. What we'll do next is change the water speed, or the pump speed, and change the water flow rate. So let's manually change this to, let's also make this 80%. So I guess a second ago we saw that this crept up to 78 degrees when we knocked our fan speed down to 80. As we knock our pump speed down to 80%, and goal seek our range, or delta T of the water, to be constant. That says now we can make 73-degree water. And again, that's the straightforward thing to say is, well, yeah, I've got less flow going through my tower. I've got less mass that I need to cool down, so I should be able to do a higher temperature difference on it. Yeah, obviously. Well, let's look at it from the graphical perspective. What we did for our L over G ratio is we decreased L. So if you decrease the numerator, then this number is going to get smaller. If L over G gets smaller, this line has a smaller slope. And if this has a smaller slope, then the area between it and the saturated curve gets bigger. And so in order to make that area equal to our target kV over L, that curve is going to have to shift to the left. And if it shifts to the left, so you're going to get colder water temperature out. Cool. So that's the effect of changing all these parameters in our model. Let's go down to this model, which uses the same set of equations, but instead of using tower fan speed as a manual input, it's calculating this based on saying, I want to achieve some water set point temperature. So what happens if we make this really low? Let's say we're serving a chiller and we want really cold condenser water. Our chiller condenser can handle 55-degree water, let's say. All right, I want 55-degree water. Well, this is saying we can only make 76.7-degree water even if I run it at 100% speed. Reason being, our wet bulb outside is 70 degrees. You cannot get a water temperature out that is colder than your wet bulb temperature out. If we look on our driving force curve here, here's your entering air temperature. If it were to exit at, if your water temperature were to exit at the wet bulb temperature, then essentially it would come out where these 2 points would be touching. This curve can never, this enthalpy path can never go above saturation. You can't have more than 100% relative humidity. And therefore, you can never get colder water than the wet bulb temperature. So that's our limiting factor. So if we're going to do some controls modifications on this cooling tower, instead of running this thing at 100% all the time, you can make this a little more intelligent and say, all right, let's look at our outside wet bulb temperature. It's 70. Let's say I know I'm never going to get 70 plus my design approach. So let's try to make 77-degree water. And as soon as I do that, my fan speed starts dropping down a bit. And you're achieving the temperature, because you're achieving the temperature you want. If I were to make this too cold, I'm not going to be able to achieve that, and you're just going to run this fan at 100% speed. I'm going to change that back to 77 and watch my fan drop a little bit. It's hard to say what the ideal control logic should be without knowing the process that you're serving here. If you're serving something like some sort of process cooling or maybe an air compressor where the colder water temperature doesn't necessarily give you any benefit, I think it makes the most sense to just set this to the maximum temperature or the design temperature of your equipment. So if you've got an air compressor where the water temperature doesn't affect the performance a whole lot, so if it's set to have a design temperature of like 80 degrees, for example, just set it to its design number, and then you're going to minimize your fan speed without affecting the process. Now, if it's a chiller, and let's make this 100%. If it's a chiller and the colder the water temperature, the better your performance is going to be. Then you're going to want this to be, let's start by saying as cold as possible. But if you get this as to the coldest that it's allowed to have as your set point, you're just going to run this fan speed at 100% all the time and burn fan energy for no reason. That's where some intelligent controls come into play and say, okay, what's my trade-off between fan power and chiller performance? Maybe my ideal is something like, for this particular case, 78 degrees, where I can ramp my fan speed down to 75% to get slightly warmer water than if it were running at 100%. Because if we're running at 100% speed, if I just force this to a low set point that I know it won't achieve, I can make 77-degree water. So let's say that if I were to make, instead of 77-degree water, just a degree higher, my fan power dropped by 6 kW. Maybe my chiller power only drops by 2 or 3 kW. So I'm not going to get into a whole optimization problem here, but just saying that there's some control strategy on your set point here that should be considered, and it's not always going to be the same depending on the cooling load that's being served. That's pretty much all that we're going to talk about now. I guess just to summarize what we talked about, the whole purpose of this is to be able to take a set of design conditions that a cooling tower is rated to do. Again, it's going to have basically these three categories here. It's going to have some outside air conditions that it's designed to run in, which are going to be worst case scenario. It's going to be able to cool some flow rate of water from a starting to a final temperature, and it's going to be able to achieve that with some amount of airflow. If you dig deep enough, they do give these fans a CFM rating that you can find. And you're going to need that to find this L over G ratio, which we've talked about too much now, but you know that's an important design parameter for doing this modeling. And so you calculate this KAV over L characteristic. Now, that's not something that's going to be published in a cooling tower spec table, but you can back into it exactly how we described. You can either use this built-in VBA code to do it, or do it kind of manually in this exercise that we talked about here. And once you know your KAV over L and your LG ratio design points, you can calculate your target KAV over L based on this equation here as your L over G ratio changes. If your L over G ratio stays constant, and it would stay constant, let's say, because your outdoor air condition's always going to change, but let's say you want to know what's the coldest water I could possibly make. Well, that's going to be running at 100% fan speed, and that's assuming you're not going to vary your condenser water or your tower water pump speed. If you vary your pump speed, your LG ratio changes, but we're saying if these flows don't change, but your outdoor air conditions do change, this number still stays constant. So then you can calculate, okay, what do my water temperatures have to be in order to satisfy this? That's the value in that Merkel equation that we talked about. Now I kind of went fast through the sheet. There's a lot more detail in here. This also looks at evaporation rate. It's calculating this without doing rules of thumb. I mean, it's finding what the actual exit air enthalpy would be, and then it's finding, okay, if that's my exit air enthalpy, what is the implied humidity ratio? And then it's taking your dry air mass flow times your change in humidity ratio to get how much water gets evaporated into the airstream. So this isn't doing the rule of thumb method. This is actually calculating it from a fundamental equation perspective. The rule of thumb, though, if you do want to do it that way, generally for every 10 degrees of water delta T, so for a 10-degree range, you tend to evaporate 1% of the total water flow rate through the tower. So easy math here, we've got a 10-degree range, so we should evaporate 1% of the flow. Our flow is 1,000 GPM, so if you take 1% of 1,000, you would get 10 GPM. And for this purpose, the rule of thumb was actually dead on. So maybe it's a better rule of thumb than I even realized. Getting our heat rejection rate, simply water mass flow. Mass flow of water is GPM times 500. And if you want it in pounds per hour, times delta T. There's also an implied times 1 in there for the specific heat. And then what we're also doing in this spreadsheet is we're looking at the power of our pump and fan. We haven't talked about that a lot, but you can assume generally that a fan is going to follow the affinity laws, where the power that the fan consumes is going to be cubically proportional to the speed that it runs at. So we're doing that more down here. This, I'm trying to take more of a realistic approach. So if you just wanted to do straight up affinity laws, what you would do is say my percent fan speed. Let's do this affinity power calc. I would say my fan speed to the power of 3 times my rated fan kW, which is this one. I would operate at that kW if I were to just straight up take the affinity laws. What I do in this worksheet to try to do something that's a little bit more realistic and a little more conservative and not as aggressive as the affinity laws is I'm assuming that the amount of static pressure that this fan has to develop is in some part due to frictional loads due to the velocity of air that it's trying to push. And then a portion of that static head that it's developing is just going to be static and not going to change. So I'm saying let's assume that 20% of that rated kW is from static that is going to be stagnant and never going to change. And then 80% is going to be proportional to the affinity law. It's doing the same thing for the pump power calculation. We have a rated pump head over here. In this case, it's 125 feet. And as you change the speed of the pump, if you're doing a straight up affinity law calculation, the head varies with the square of the flow. So if you're doing a straight up affinity law calculation, you do your percent squared times the original head gives you your new head. To be more conservative, this is assuming that this 125 feet is 20% due to static head, which is not going to change ever, and then the other 80% is due to dynamic friction losses. I find that's a little bit more realistic than just doing a straight up affinity law calc. I hope that helps, and good luck.